Hey, welcome back. This is the second video about flux integrals. This is going to be a bit of a shorter video where we'll start by reviewing what we talked about last time, and I'm going to show you a way that you can make the flux integral calculation go a bit faster in some circumstances. All right, let's go. All right, so here's a review of what we talked about in the previous video. We introduced flux integrals, which again is a measurement of how much a three-dimensional vector field is flowing through an oriented surface. And this was the notation for it here, the integral of f dot ds. And the way that we defined them, the way that a flux integral is defined, is via a scalar surface integral. In other words, at every point on the surface, we are looking at the dot product of the vector field with the unit normal vector to the surface. That's a number. And so this is a function that we do a scalar surface integral of over the entire surface. So we're really trying to find a net measurement of how much f points in the same direction as the unit normal from the surface. Remember that there's this piece about the orientation of a surface, because at every point on the surface there are two different normal directions. And so the orientation was how we specified which one we were interested in. It was how we specified which direction through the surface we wanted to count for positive flux. Now, after thinking a little bit about what it would be like to compute this scalar surface integral, we came across a formula that we could use from a parameterization of the surface, which says that if we have a parameterization of the surface, r of u and v, then we can compute the flux integral by taking a double integral over the parameterization domain. The integrand is f of r of u v, so we're writing the vector field in terms of u and v, dot ru cross rv, which was the normal vector. And remember, we took plus or minus ru cross rv, depending on whether or not this normal vector pointed in the same direction as the orientation of the surface that was specified in the problem. So this formula is a great way to calculate flux whenever you can parameterize the surface, but you've probably already seen already that it's a bit tedious to calculate. There's a lot of little mini steps that you have to do. So what I'm going to show you now is actually a situation in which it makes sense to calculate flux by going back to this definition in terms of a scalar surface integral. So let's get into an example that actually illustrates that. So we want to compute the flux of this vector field, x, y, z, through a disk, and this disk is the disk in the plane x equals 3. It has radius 2, and it's centered at the origin. And we've specified that the normals for this disk are going to point in the negative x direction. I'm going to show you a picture really quickly of what this situation looks like. Okay, so here's this vector field xyz, and you can see that it's sort of this vector field that's pointing away from the origin at every point, and its magnitude gets larger as you move away from the origin. And this surface here, this is the disk of radius 2 in the plane x equals 3, centered at the origin. And I've drawn it in with a blue and a yellow side, just like in the previous video, to remind us that this surface has an orientation, which is from the yellow side to the blue side. Remember, the problem said that the normals are pointing towards the negative x direction, so they'll be pointed from yellow to blue. And we want to compute how much this vector field is flowing through this surface in the direction of the orientation. And you can see from the picture that since these vectors are pointing in the positive x direction, and the surface is oriented in the negative x direction, we expect the flux to be negative. Now, we could compute this flux integral by the same method from the previous video, which was we could parameterize the surface, and then we could compute that f of r of uv, we could compute ru cross rv, and then use the formula that we just reviewed. But there's actually going to be a simpler way. Let me show you what I mean. I'm going to write down, just to start, the notation for the flux integral that we're computing, and the definition of flux in terms of a scalar surface integral, meaning that we are going to, at every point on the surface, look at the vector field dotted with the unit normal vector, and integrate that as a normal scalar surface integral over the disk. The thing to notice here is that this unit normal vector is not something that we need to parameterize the surface to compute. Remember from the picture I just showed you that this is a disk just lying in the plane x equals 3. So a normal vector that points in the direction of the orientation is the vector -1, 0, 0. This is a unit vector, and it's pointing in the negative x direction at every point. So we can use this as the normal vector in our calculation. Now, if we do that, let's think about what this integrand will end up being. We're taking the dot product of the vector field xyz with -1, 0, 0. And so we're just going to get negative x. And so the flux integral that we were trying to calculate now, we've reduced it to a scalar surface integral of negative x over this disk. But wait, there's actually more here, because we're looking at a disk that lies entirely in the plane x equals 3. So for every point on our surface, x is equal to 3, and that means that the integrand we can write as just negative 3. And that's because x is equal to 3 on the entirety of our surface. So what we have is actually a scalar surface integral of just negative 3 ds, and now we can use some of our knowledge of scalar surface integrals to evaluate this. In particular, we can take this constant negative 3 and pull it outside of the integral to turn it into negative 3 times the scalar surface integral of 1. And now we remember that the scalar surface integral of 1 over any surface is just going to be the area of that surface. And since this surface was a disk, we know how to calculate its area. It was a disk of radius 2, and so what we'll get for the area is pi times the radius squared. And so the flux integral is equal to negative 3 times 4 pi, which is negative 12 pi. So this was what I was referring to. By thinking of a flux integral as a scalar surface integral of f dot a unit normal vector, in this situation, because of how the vector field related to the surface, we were able to shortcut the parameterization process for computing flux, and just note that this dot product was actually always constant. And so the flux integral ended up being just a constant multiple of the area of the surface. This might seem like a special case, like maybe I engineered this problem to specifically work out nicely like this. And yeah, I did. But you'd be surprised actually how often it comes up in situations like physics and engineering where you're trying to calculate maybe the flux of an electromagnetic field through a sphere, right? Situations in which the vector field is completely perpendicular to the surface at every point. And so you're able to find an expression for f dot n without parametrizing. Okay, so I'll leave you with this summary, which is actually kind of the review from the beginning of this video, just written backwards. The point of this video was really to show you that we can always compute flux by parametrizing a surface and then using this formula. But in certain situations, it's faster and more efficient to think of the flux calculation via the scalar surface integral definition. Because if this integrand is constant, then you can find the flux integral by just multiplying this constant by the surface area of the surface, which saves a lot of time. Now, I can imagine you might be wondering right now, how can I tell which of these two approaches to use when evaluating a flux integral? For now, I'll just say it's going to be something that will become clearer as you keep practicing. Once you have a better sense for what a flux integral actually represents, you'll be able to see situations in which you can more efficiently compute it. All right, happy practicing, thanks for watching, and I'll see you in the next video.